In the last video, we talked about rank of a matrix, and there we looked at a matrix as a collection of columns. And later we also saw that we can as well think of a matrix as a collection of rows. Now, there are basically four different ways in which you can consider a matrix. The first one is just as a rectangular array of numbers. That is basically how matrices are introduced to a kid. This has hardly any mathematical content. The second is what we have used as a bunch of vectors, either stacked together as columns or stacked together as rows. The third one is the most important. It is as a linear transformation. And the fourth one, which is useful especially in statistics, where a matrix, in particular a real symmetric matrix, is considered as specifying a quadratic form. In this video, we shall consider the third representation, namely thinking of a matrix as representing a linear transformation. So let's first familiarize ourselves with the concept of matrix and a linear transformation. Now, any linear transformation, like the function that I showed, x being mapped to ax, is a function. And whenever we talk about a function, we must have a domain and a codomain. So in this case, I consider this as my domain and this as my codomain. So in this case, the way I mentioned it, I take this to be Rn and this to be Rm. So there is a map from Rn to Rm. So we are taking this map. Given any vector here, I multiply that from the left with the matrix A and I get something here. The way I have shown, you can easily see that I am not claiming that this is an onto map. So part of the codomain is left out. So the part of the codomain which is used, where this blue thing is hitting, that is the range. So far there is nothing special about matrices. This is true about just any function out there. I have a domain, I have a codomain, I have a range. Now, since we are working with matrices, as a result, both the domain and the codomain, they are vector spaces. Also, the range turns out to be a subspace of the codomain, which is pretty easy to check. Now, because it's a vector space, so there is a zero vector. There's a zero vector, of course, both in the domain and the codomain. We need the zero vector in the codomain. That's what I have shown with the red dot. That's the zero vector. Now, various vectors in the domain gets mapped to that. So, if we go back from the zero to the domain, in that case we get a subset of the domain that is mapped to that particular zero vector, and that set is called the kernel. Okay, so we have this setup that we have got this space, which is the domain, the codomain, and we have the range, and then inside the domain we have the kernel, the set of all vectors in the domain which gets mapped to the zero vector. So this is the setup. This picture you must just fix inside your brain in order to follow the rest of the lecture. So we have this picture. We have got domain, codomain, kernel and range. Let's clearly understand what are the different dimensions of these various quantities, of these various subspaces. The dimension of the domain, it should be quite easy to see that it is equal to the number of columns of A, because if A is m cross n, then this can multiply only a vector in Rn, otherwise you cannot even do the multiplication. So this has to have dimension number of columns of A. Similarly, the codomain has dimension number of rows of A. These two are pretty simple. Now let's look at the range. What is the range? Range is the set of all vectors that are of the form A times X. Now we already know A times X means linear combination of the columns of A. That is, the set of all vectors of the form A times X is precisely the column space of A. That is, the range is nothing but the column space of A, and its dimension we have already given a name to, namely the rank. So the dimension of the range space is the rank. Now we do not have any special names so far in our lecture for the dimension of the kernel, so we just give a new name, we call it nullity. Nullity of the matrix denotes the dimension of the kernel of this function. Okay? Now there's a very strange fact that relates all these things, and that fact is, if I add the dimension of the range with the dimension of the kernel, then I will get the dimension of the domain. The dimension of the codomain, by the way, does not play any role in this drama. Now this fact is pretty strange because the domain is here and the kernel is here. So domain and kernel, they are sort of understandable, one sits inside the other, but this range that sits completely elsewhere in a different world, why should the dimension of this plus dimension of that should have even any interpretation? But it does have an interpretation, and it is actually equal to the dimension of the domain. So it is one of the surprising facts of linear algebra. And it is very useful too, so some authors even go as far as calling it the fundamental theorem of linear algebra. Now the result is strange, but it is very easy to prove. Once you know the result, to prove it is very easy. What we do is the following. We just start with some basis of both the kernel as well as the range. So suppose I take the kernel has got dimension 2, that is nullity is 2. So I take any basis, that is two vectors in the kernel which forms a basis. Similarly, suppose the range space has got dimension 3, that is rank of the matrix is 3. So I take these green vectors which are all inside my range space. So I have got 5 vectors. If somehow I can say that these 5 vectors together form a basis of the domain, then I am done. Because then I can say that the dimension of the domain is 3 plus 2, that is range plus kernel, range plus nullity. Rank plus nullity. The only problem is that I cannot really say take these green things and these kernel basis, put them together. You cannot put them together because these sits inside Rn and those sit inside Rm. I need all of them to be inside the domain before I can even claim that they form a basis of the domain. They must be at least be in the domain. What can you do? The most obvious thing works. Remember, you have this map. This map takes things in the domain and puts them into the range. Now these green dots, these vectors are in the range, which means there are corresponding vectors in the domain whose image are these things. Now they may not be unique, they will not be unique in general. The way I have drawn, it is not a one-to-one map. So I cannot say I am taking the inverse of that. Because you see, here I have so many vectors all mapping to 0. So it is not one-to-one, but for each one of them you can get one point here which is mapped to that thing. Such a thing is usually called a pullback. So what I do is for each of these 3 I get a corresponding pullback. They are not unique. Pick any vector here such that if you multiply that with A, you get this. Take any vector here, if you multiply that with A, you get that, and like this. For each of these 3 I get this thing. Now I have got 5 vectors all sitting inside the domain. You understand, this entire construction involves a number of arbitrary things. First of all, I picked some arbitrary basis of the kernel, some arbitrary basis of the range, then some arbitrary pullbacks of these things. in spite of all this arbitrariness, howsoever you do all these things, you can check and pretty easily, just 2 or 3 line argument, that these 5 vectors will be a basis of the domain. I leave that as an exercise, very simple, just show that they are independent, then show that they span the entire domain. And immediately you see that the total number of basis vectors that you get for the domain is number of basis vectors for kernel plus number of basis vectors for the range, that is rank plus nullity equals the number of columns of any matrix. A surprising fact.